Welcome to lesson B-17. In this lesson, you'll learn how capacitors work and how to use them in a circuit. You'll also learn about the capacitive touch sensor included in your kit and how it can be used in future projects. In this video, we'll start our deep dive into capacitors, including how they work and their current limiting abilities. In the next video, we'll look at charge time and working with capacitors in parallel versus in series. We'll then move on to look at how to use a capacitive touch sensor, as well as working with male to female jumper wires. Capacitors are used to quickly store and discharge energy into other components. The amount of energy a capacitor can store is known as its capacitance. Capacitance is measured in a unit called the farad. But most of the capacitors you see in projects will be measured in millionths of a farad, called a microfarad. The symbol used to indicate a microfarad is UF. The capacitance value determines how much energy can be stored in a capacitor. A higher value indicates that it can store more energy. So a 2200 UF capacitor can store around 10 times more energy than a 220 UF capacitor. Capacitors store energy by using two foil plates separated by an insulating material like paper or plastic. In tiny capacitors, this may appear like a tiny foil or plastic sandwich, but in larger capacitors, the sandwich is rolled up. This helps minimize the horizontal size of the component. Smaller capacitors are often not polarized, so they can be used in a circuit in either direction. Larger capacitors, known as electrolytic, are polarized though and must be placed in the circuit properly to avoid damage to components. The negative of an electrolytic capacitor will be marked with a minus sign and often a large gray band. A capacitor will try to charge or discharge as fast as the electrons can move in and out of the device. When initially connected to a supply voltage, a fully discharged capacitor will act like a short circuit to your voltage source. Current will rush in to charge the capacitor as fast as possible, and if this amount of current exceeds what your power supply can deliver, the supply could be damaged. The same type of damage could occur during the discharge of a capacitor. If you connect a fully charged capacitor directly to a low GPIO pin, the grounded GPIO pin will attempt to provide a current path for the charge inside the capacitor. If the current in or out of a GPIO pin exceeds 16 milliamps, then it could be permanently damaged. Instead, a current limiting resistor should be placed in series with the capacitor. Using the supply voltage and the value of the series resistor, you can then calculate the maximum amount of current that will be allowed to flow in and out of the GPIO pin. Now, you calculated current using a series resistor with an LED back in lesson A3, but calculating current in a series resistor attached to a capacitor is slightly different. Unlike an LED, a capacitor will not create a voltage drop in a circuit, so its forward voltage is essentially zero. This means the entire source voltage will be dropped across the resistor. So in this example, an LED drops 2.8 volts of the 3 volt supply, leaving only 0.2 volts to be dropped across the resistor. Ohm's law shows that a 220 ohm resistor in this configuration will limit the LED current to around 0.9 milliamps. Here is the same circuit, but the LED has been replaced with a capacitor. Since the capacitor has a forward voltage of 0, the entire supply voltage will be consumed by the resistor. This results in much higher current running through the circuit, despite both circuits using identical supply voltage levels and current limiting resistors. This is why a 1000 ohm resistor will be used as a current limiter in the upcoming activities. So looking at these equations, GPIO voltage divided by the current limiting resistor equals current running through the GPIO pin. So that's 3.3 volts divided by 1000 ohms equals 3.3 milliamps. This will limit current flowing through the GPIO pin to 3.3 milliamps, which is safely below the limit of 16 milliamps for the GPIO pin. Okay, before we move on to the next video, let's take a few moments and review the concepts we've just discussed. First, we talked about capacitors as being able to quickly store and discharge energy into other components. There are different sizes of capacitors available. The 2200 UF capacitor in your kit can store 10 times the energy as the 220 UF capacitor in your kit. While smaller capacitors may not be polarized, larger ones, known as electrolytic, are polarized. Be sure to identify the negative of the capacitor by the gray band and place it in the circuit in the correct direction. Capacitors can charge and discharge very quickly. To protect the power supply in the GPIO pin, it's very important to place a current limiting resistor in series. For the activities in this lesson, you will use a 1000 ohm resistor to moderate the current to 3.3 milliamps, which is well within the safety limits for the Raspberry Pi. Okay, go ahead and move on to the next video for this lesson, where we'll continue to talk more about capacitors, including charge time and working with them in parallel versus in series.